Hello and welcome to my talk about the stability of a standing molecule and its dynamic properties. My name is Christian Wagner and I'm from the Jülich Research Center in Germany. Now, in the previous presentation, I showed you how we can actually manipulate individual molecules and access the third dimension. And I would really recommend that you watch this video first if you haven't seen it yet. So we want to build into the third dimension because it decouples basically the molecule from the surface and therefore preserves any intrinsic molecular functionalities. And of course, this is very important if you want to build molecular machines, motors, switches, and so on. But of course, there's also a downside because these structures are rather complicated to make and typically rather fragile. Something interesting that we were able to construct recently by single molecule manipulation is such a standing molecule on a metal surface. And I would like to discuss how fragile this structure actually is and also briefly comment on its dynamics. Now, my colleagues Ruslan and Tanner, they were recently able to fabricate such a standing molecule by first constructing a pedestal of two silver atoms at one end of the molecule, and then contacting the other end, and by retracting the tip, then lifting the molecule into a vertical configuration. And since the bonds at the bottom of the molecule are stronger than the bond at the tip, you can basically break this one here by simply retracting the molecule and then, retracting the tip, and then you have a standing molecule. Now, there's one more important thing, because there are two slightly different configurations of this atom pedestal where the atoms occupy different sites on the surface and with slightly different distances. So this will become important in a minute. But first, I would like to show you the tip-molecule interaction. By the way, here everything is drawn to scale on this figure. And we measured the interaction in two different directions. Once in the plane of the molecule and here vertical to the plane of the molecule. And you can see a clear difference between these two plots. On the right-hand side, the potential energy landscape is much wider, which actually clearly indicates that the molecule is tilting always towards the tip. And so it's not very stable. Because we are in fact talking about very small energies here, well below 100 millieV, which means that to understand the intrinsic molecular stability, we have to get rid of the tip, we have to retract the tip far away, but then of course we cannot interact with the molecule and also not excite it. Now the solution which we found is thermal excitation. We basically raise the temperature above our 5K base temperature, then we remove the tip and wait, and after a time T up, we return the tip to the molecule, and then there are two possibilities. So either the molecule is still standing or it has actually collapsed. And then we repeated this experiment about 1,000 times, and here you can see now a plot of the molecular survival rate as a function of temperature. And indeed, for the two different pedestals, you have two different survival rates. But in any case, PDCDA collapses still at a very low temperature, right above 10K. Now, we can also plot the data in the form of an Arrhenius diagram of lifetime versus temperature here. And from transition state theory, we can now also plot the curves that we would expect for various magnitudes of the stabilizing potential. And as you can see that in our data, this potential is somewhere between 26 millieV and about 31 millieV, depending on the type of pedestal. And what's really striking, if you now compare this to theory data on the level of PPE DFT plus many-body dispersion, then you can see that the theory is really spot on with just like a single millieV of discrepancy. And of course, this is very surprising, but it probably has to do with the fact that we are talking about energy differences here and not about absolute energies. But in any case, this result really gave us the confidence to use PPE plus MBD as the basis for the configuration monitoring that I mentioned in my previous talk. And since now the theory seems to describe the experiment pretty well, we can actually use it to understand what stabilizes the molecule. And for that, we split the calculated energy into two contributions, the covalent part, which turns out to be strongly stabilizing, and the van der Waals part, which tries to bring the molecule down, so it's destabilizing. And that is the long-range molecule surface interaction, basically. And it shows that we have a very delicate balance between stabilizing and destabilizing interactions. And here in the middle, this is the sum of both contributions, the potential that actually is a potential well and stabilizes the molecule. And I also promised that I would say something about the dynamics. And we haven't measured that directly yet, but we can calculate that in this potential energy landscape, it's clear that the molecule is something very interesting, namely a mechanical oscillator in the range of well below 30 gigahertz, which of course is an insanely low frequency for a molecular vibration and could be something very interesting in the future. Now, the second part which I would like to talk about is that of design. So how can we engineer molecular stability? And for this, we have changed the configuration a little bit and looked at the stability of PTCDA on various SPM tip configurations that you can see here. And this is relevant for us in two respects. First, it helps us to understand the stability mechanism better, but it also is relevant for SQDM microscopy technique, where the molecule is on the tip, as I showed in my previous talk. So, and here you see this number of different tip models, where we always took a pyramid and cut it at a certain height and then placed two adatoms here in black as the tip apex. And this now somewhat resembles the molecule standing on the surface that I showed previously. And interestingly, in all these cases, you get more or less the same stabilizing potential from PBE for the chemical interaction, even if you place the orange curve here, place the molecule on a bare surface without the pedestal. On the other hand, the destabilizing van der Waals potential actually, as you can see, differs strongly between the different configurations. And of course, this is simply because the long-range van der Waals interaction depends on how many atoms there are in the close vicinity of the molecule. So it's no surprise that the lowest van der Waals potential here in gray is achieved for a very sharp tip, whereas the molecule on the bare surface without the pedestal has the maximum of destabilization. This is the orange curve. And to explain that, we developed a rather simple model of two dipoles, where the dipole associated to the adatom pedestal, this one, is basically parallel to a local molecular dipole. And this is, of course, energetically favorable and provides stability, this parallel alignment. And indeed, our model well compared quite favorably with DFT data in terms of the molecular tilt angle, but also the energies involved. And finally, we performed a computational case study to improve our understanding and basically validated these ideas. And first, we tried the smaller anti-CDA molecule and found that actually the destabilizing van der Waals potential is very similar to PTCDA, which is surprising at first glance, but it basically means that the upper part of PTCDA, which is kind of extra here, contributes only very little to the destabilizing van der Waals interactions because it's already too far away from the surface. And then to test our dipole model, we introduced a pedestal of platinum atoms instead of silver, which actually has an opposite dipole compared to that of the silver pedestal. And indeed, there is no stabilization if you put PTCDA on the platinum, which kind of confirms our model. And with this, I would like to conclude. So we have used single molecule manipulation to create these metastable structures where the molecule is decoupled from the surface. It's a very weak stabilization, and DFT gives us a very high prediction with very high accuracy of the stabilization. And to engineer and specifically to increase the stability, first you have to minimize the van der Waals interaction, which you could either do by using a very small molecule or a narrow pedestal, in the sense that tip apex is also some kind of pedestal. And on the other hand, of course, you want to provide directional chemical bonds. And with this, I would like to acknowledge all my coworkers and collaborators who have contributed to this research. And since unfortunately you cannot ask any questions, please feel free to contact me via email. So thank you very much.